are we doing today? The exact same thing, except we're going to go through and change temperature. Okay? Why are we changing the temperature? So what we're attempting to do is to figure out the temperature dependence on our rate. So how is temperature related to rate? Because I don't have a whole lot of space, I'm just going to abbreviate things. Okay? So that's kind of our intent, trying to figure out what's going on with that. Okay? How are those two connected to each other? Okay? We do have some ways of sort of cheating on this because a lot of that relationship has already been discovered. Okay, so what we would be looking at is the Arrhenius expression, which I think I spelled right. And we know that our rate constant, try and make that look like a small k, equals a to e to the negative e over rt, okay, where T is our temperature and K is our rate constant. Okay? One of the things that's interesting from this expression is we can also determine the activation energy. So that is going to be characteristic for our reaction. Now we can potentially change temperature, change our rate to improve the speed of our reaction. So we could get out of lab faster by changing that temperature. Okay? So it's one of the reasons why we're going to go through and do this is if with that information we can then go through future labs faster. It's kind of the intent. Okay, so we want to try and evaluate, get as much information about this reaction as possible. Okay, what information would we need to determine the activation energy? Okay, so what are our complications? Based on this equation, what information do you need to know? We need to know temperature. Is that necessarily a complication? No. Why not? Temperature is relatively easy to measure, so it's not that big of a complication. That said, that temperature needs to be constant throughout the reaction. Okay? So it's not so much that measuring the temperature is a complication, but making sure it stays constant. How do we do that? Hot plate and ice. Okay? Our hot plates are notoriously awful. I almost always, both in 152 and in organic, get students ask, well, what setting do I set it to? I don't know, on. See what happens. Right? A lot of the hot plates, you're looking at, usually the ranges are 1 to 4. Okay, what is 1 and what is 4? With a lot of the hot plates, those numbers are meaningless as well. Okay? In general, what they're supposed to be is 1 is kind of on, 4 is really on. Okay? That's about it. The more on it is, the more heat is generated, the hotter it gets. Okay? That's kind of a general rule of thumb. That said, a lot of the circuitry is busted within some of them. You turn them on, and it immediately jumps to all the way on. Okay? So you're going to have to kind of play around with your individual hot plates to figure out where the ultimate setting is to maintain those certain temperatures. Okay? For this experiment, we're looking at 40, 30, and 0 degrees. You won't use the hot plate for the 0 degree one. Just figure to throw that out there. Okay? So you'll have to kind of work with that as best you can. And I'll mention, maybe I'll mention this. The 40 degree one I think is the one I would start with. So as soon as you get in there, get a hot or a large beaker, fill it with water, and immediately get it on the hot plate, trying to get it up to 40 degrees. Okay? Because that's going to take the longest time to get to stabilize. Get that started right away so that hopefully by the time you get your solutions, you've got it stable so you don't have to wait for that heating process. Once you've done the 40 degree one, you can take the water bath off or turn the heat down and try and get it to stabilize at 30. While you're waiting for it to stabilize at 30, you can shift and do the 0 degree one. Okay? So you can hopefully maintain those temperatures as appropriately as possible. Okay? What happens if the temperature changes? Your calculations are wrong, and ultimately your experiment fails. Okay? So what we want to do is maintain those temperatures as best we can. Okay? What else could be a possible complication in this? Do we know what R is? Gas constant, so we can figure that out. or look that up. The activation energy is something we're trying to determine. A, do we know what A is? It's our frequency factor, or ultimately a measure of the success rate of our reaction actually progressing forward. So it's a collision factor. We don't know that number. Okay. Do we know the rate constant? No. Okay. We could determine the rate constant at 25 degrees or 20 degrees, whatever your experiment was last week, because you were able to get that. You got the rate constant. But we don't know what it is at each of these temperatures. Okay, so that's a potential complication of this. So we'll address some of these issues here. Okay. This equation or this format for this equation is not the easiest to manipulate. If we try to go through and plot this, first off, we'd probably make lots of mistakes when trying to enter it into the correct formulas to be able to interpret information. And if there was a mistake in our experiment, we wouldn't be able to see that mistake as easily. So we want to rearrange that equation to set it up a little bit easier to manipulate. What do?
Log or natural log.
We'll take the natural log of both sides to get rid of that E value, and we'll get the natural log of our rate constant will equal negative A over R, 1 over T, plus the natural log of A. Okay? This new equation can help us a little bit more because it is the equation of a straight line. So if we plot y equals mx plus b, I don't need to know A if I can figure out what my temperature is and what my rate constant is. Okay, so the temperature we said we can measure. A is now irrelevant. Our rate constant. There's a bit of a problem. How do we solve for the rate constant? How did you solve for it between Tuesday and today? Wait, today is Tuesday. Today's Tuesday? How did you solve for it between Thursday and today? We took all these logs and all these other fun things to determine the order. So our experiment last week was ultimately to determine the rate law. Once we knew the rate law, we could then solve for the rate constant. Since we're running the same reaction, what's the rate law for this experiment? The same as the rate law for the last experiment. Okay? So what we would need to be able to do is determine the concentrations. So if we go through and look at our rate expression, we have rate equals K times concentration of iodide to its power, concentration of peroxide to its power. So one of the things that we need to be able to solve for our activation energy is the rate constant, which means we need the rate law. The rate law, because we're doing the same experiment, or the same reactants, will be the same regardless of our temperatures. The only thing that will change will be the rate. That means if we know the rate at each of our temperatures, and we know the concentrations at each of our temperatures, and we know the orders from last week, we can now determine the rate constant for each of these new temperatures. Okay? Kind of vaguely makes sense. We walked through that really fast. So here's what you're going to do. You're going to do the exact same experiment, except you're going to monitor temperature at the same time. Then you're going to go through and do the exact same calculations that you should have done already for part A, okay, to get your rate constant. Once you've got the rate constant, now you can actually move on to today's experiment, and you will plot the natural log of the rate constant versus 1 over temperature. That plot should give you a straight line. What is the slope of that straight line? Negative the activation energy over R. We can now solve for the activation energy. Okay? We can also solve for A. Okay? How could we solve for A? What do we know the natural log of A is equal to? B, which is the y-intercept. How do we solve for A? E to the B gives us A. Kind of makes sense? All right. A lot of this is going to be difficult to see at this point because you can't see anything. There's no calculations, there's no results to really look at yet. All right. So we're going to open up the Excel file here in just a little bit just to make sure we can see everything. So one of our primary complications of this isn't so much a complication as it is realizing that we have to do part A first before we can do part B. So one of the lead-ins that you could do in your report is talk about part A and then say, once we have the rate law, what can we do with that? Now we can change temperature and compare that back to our rate constant to determine the activation energy for the overall reaction. All right, so we can get kind of a smooth lead-in our introduction. Questions about the equations that are tossed up there? Okay, so what we're going to end up doing now is walking through all of the almost now. Your table for this lab should look almost exactly the same as for the last lab, except you're going to have an extra column for temperature. You're supposed to target 40, 30, and 0 degrees Celsius. You do not have to hit them exactly, but you do need to record exactly what they are. Does that make sense? So make sure you got your thermometers in those water baths and you're monitoring them. Right? All of our solutions are still in the back room. Use those procedures as your guides for your volume. The hot plates are in the cabinets closest to here, which might have been nice to tell you a lot earlier, like when we did the titration lab, so they weren't as hard to find. But they are right here. And then it is difficult to maintain that temperature. Okay? You're just going to have to kind of fight with that as much as possible, or hopefully minimize your anger as best you can. Okay? But there's not a lot we can do about that. Okay? So, as to these calculations, I closed it. We are going to open up the exact same file that we had before. Maybe. Yes, there it is. So you guys should, because you all did part A calculations already. Whoop, not that. Should be familiar with this file. Okay, it is posted to Canvas. You do not have to use it. It's just highly recommended. It's going to be the easiest way to go through and solve everything. You'll notice the very beginning of it, you've got all of your experimental data, followed by the total volume, which we talked about how you could enter that, and your time. Okay? You've then got all these extra little cells that you can then fill in. The very last thing that you would solve for part A is the rate constant. Because we are going through and repeating these calculations with respect to temperature, we could go through and delete all the work that we did, but then we'd lose all of that. So what I've gone through and done is copied it over into a second worksheet. So if you go to the lower right-hand corner, you should see that second worksheet tab, and you'll open up rate B. How's the size on that? Can you guys see that okay? Sounded like a bigger. We'll go a little bit bigger. You'll notice we get the exact same format as before, all of our individual containers and our volume. I've added a column for the degrees Celsius, your temperature reading. The next thing you'll notice is there's a K1 right next to it. What does K stand for? Kelvin. Why do we need the kelvins? Our temperature in the Arrhenius equation is in units of kelvins. Okay, so you must do that conversion. Okay, I need to copy some data over so we can work with some of this. To get the total volume, what did I say we do? We want Excel to calculate it for us, so we'll hit equals. We can then click individually each cell that we want it to add up, and it will just add them to it. The other option is doing that sum option that we talked about last week. If we hit return, it gives us the sum, a click and drag for as much as we've got data, we'll now repeat that calculation. Since we're clicking and dragging downwards, the only value that Excel will change will be the rows, the numbers. It will not change the columns because we're clicking down within a column. Okay? Temperature. Let's say these were 40 degrees. How do we solve for our Kelvin temperatures? It's our temperature plus 273. Relatively simple calculation. You could do it on your own, or you can have Excel click and drag for you. Okay? Time. It's in seconds. I was going to give a number. I unfortunately do not know any of the times for these individual experiments. We would expect the 40 and the 30 degrees to react faster, but I don't have an approximation. So we'll just come up with some random time value and just enter those. Okay, let's say 400 and 390. Why did I pick two times close to each other? Trial 1 and trial 2, both at the same temperature. I think there's some concentration changes, but it's not a lot. Okay, so we would expect those times to probably be pretty close to each other as a guess. Okay, as soon as someone gets a time reading for your individual temperatures, let me know and I'll start writing them up on the board. So those coming a little bit after have an approximation on when to see that color change. I pulled the concentration of iodine out as a separate thing in this case. We don't have to pull it out separately, but how would we calculate it? How did we determine the concentration of iodine in our previous experiment? It's dependent on our thiosulfate. So it's the volume of thiosulfate used times the concentration. Because the concentration is something we want it to always refer back to, there's two ways we can approach this. We can put the money symbols in. So now Excel will always refer back to that. The other way, which a few students have discovered, just put in what the concentration value is. Now you don't have to worry about cell references. Okay. That gives us the moles of thiosulfate added. What's the relationship between the moles of thiosulfate and the moles of iodine? Not 1 to 1, 1 to 2, but I don't remember which way it goes. So we'll want to multiply by 0.5. I'll leave you to actually discover that on your own. That now gives us the moles of iodine if we want the concentration. We want to divide by the volume. What volume do we want to divide by? The total volume of the entire solution. So we can now go to our total volume column, click that, and we now have our iodine concentration, and we can click and drag. Okay? Assuming that conversion was done correctly. Sound good? We can now move over to our iodide concentration. How do we determine that? The amount of moles we added, so the volume times its concentration, which I'll leave as 0.3, divided by our total volume, and we now have our concentration for iodine. Our concentration for peroxide, same general idea. It will equal our volume for our peroxide times the concentration divided by the total volume. We can click and drag. Our rate is equal to concentration of iodine divided by the time. Turn, click and drag. Our rate constant. What is our rate constant equal to? Well, we know rate, let's go with a different color. Rate equals our rate constant times our concentration of iodide to the, I'm going to go with P power. Sounds kind of funny. P power. Sorry. Times the concentration of peroxide to the Q power. How do we know what P and Q are? We did the experiment from part A, so you must do those calculations first, since I know you guys did it. What did you get for P and Q? Okay, it should come out approximately 1 and 1, because I know it's going to be decimal values and I don't want you rounding. Let's make it a decimal value. Let's call it 0.923, 0.989. How do we solve for our rate constant? K equals rate divided by I minus the 0.923 times H2O2 to the 0.989. That's our formula. We would now have to enter that into Excel for our rate constant. Okay? I noticed a couple groups trying to go through and enter this in Excel. An experienced group, someone that actually knew how to use Excel already, failed to enter this formula correctly. You must be careful. What's a quick, easy check to verify that you entered your formula correctly? Could go through and do it by hand as a check. That's not very quick. From part A, what should your rate constant be for all of those trials from part A? The same. If it's not the same, what does that mean? There's two options. Your experiment was wrong or you entered it into Excel wrong. Trust your experiment. It's probably you entering it into Excel wrong. Okay? So I'm going to attempt, we now have to clear out of this to enter this in. Our rate constant, we said, was equal to our rate divided by, we need to make sure we include our parentheses here. The Ki, to get it to the power, we'll do the caret. What did I say Ki was? 0.923 times our peroxide to the Excel should be able to do the order of operations appropriately as I entered it in there with only one set of parentheses. If you don't trust Excel or for some reason you get weird results from part A, you can add more parentheses in. Make sure at very least that those or that bottom part is in its own set of parentheses. Okay? Otherwise you'll end up dividing by, in this case, R8 and then multiplying by S8. Which is wrong. It needs to be a division all the way through. Okay? That gives us our rate constant. We can click and drag. Would we expect the rate constant to be the same here? Probably, because temperature is the same, and depending on the experimental procedures, the concentrations are the same. The concentrations in the one that I picked weren't the same, so we would expect a different rate constant. Okay. All this does is get us back to where we started. Okay. Now what we've got to do is actually propagate this further to this part of the experiment. For this part, we will take 1 over our temperature. So 1 equals 1 divided by our temperature in what units? Kelvins. Make sure you use the correct one. We can do our click and drag as well. We can plot that versus the natural log of our rate constant. To do that, equals ln parentheses, click on our cell, return, click and drag. Okay. We will plot 7 data points here instead of 6. Why do we have 7 data points? What's that extra 7th trial? Part A. Okay. Part A, you did monitor the temperature. It was roughly 30 degrees, something like 27 degrees. You will take that rate constant and that temperature and propagate it over to this experiment. So there should be 7 data points on your graph. If they're not, you didn't do the experiment right and you'll lose points. Okay? So we will then take those 7 data points and make a graph. Make sure the graph you're using is a scatter plot. if you use the file that I've got set up, right-clicking within that graph, select data, you can add a series. Our x values are our 1 over temperatures. Our y values are our natural log of k. We would select all of that data. I only have 2 data points. Okay? We would then click OK, and we see our data plotted. Okay? We would then right-click on all of the data, add Trendline. Whoops. Heck, why is it not popping up? Oh, man. Why is it not giving me my option? I do not know why it is not allowing me to add a trend line neatly. You should see an option pop up saying that you want to fit it linearly and you want to see the equation of the line. I'm going to guess, because I only have 2 data points, maybe it's not letting me do that. As far as what your graph will look like, just to give you an idea, you should see 2 sets of data followed by something along these lines, and then one kind of floating in the middle. Your equation of your straight line should ideally hit somewhere straight through that. Okay? That is approximately what your graph will look like, okay, if everything goes perfectly. Excel will then give you the equation of the straight line equals negative, let's say, 4,000 x plus, it's going to say minus, let's say it's 7. Oops, I plotted it the wrong direction, didn't I? Yeah, for it to be a negative slope, it needs to go the other direction. Sorry. We're going to see a plot this way. So 2 data points, 2 data points, 1 lone one, 2 data points. It should give you a negative slope. Okay, that is negative, isn't it? Okay. Why should it be a negative slope? Because according to our equation, m equals, in this case, negative 4,000, which equals negative activation energy over R. What's the sign on R? Positive or negative? Positive. If we get a positive slope, what does that mean our activation energy is? If we get a, in this case, when we go through and do the math, we would get what sign for our activation energy? Positive or negative? Negative and a negative is positive. Okay. If our slope for some reason comes out positive, what sign do we get on our activation energy? Negative. What did our activation energy refer to in our energy diagram? It referred to this barrier. Can that barrier possibly be negative? No. So if you get a negative value for your activation energy, you did something wrong with your calculations. Go back and check. Your activation energy should come out to be positive. Okay? That's actually everything. That gives you your activation energy. Officially, you should calculate A as well. How do you calculate A? E to the B. So E to the B in this case would be E to the negative 7. And you would solve for it. Okay? Lots and lots of calculations, lots of manipulations. Most of them were manipulating the mathematics into formats that we can interpret a lot easier and then be able to pull our information off those graphs. Okay? It requires a bit of work. If you've got questions with it, feel free to ask. I would recommend that you go back through and try and watch the videos to help out with it. You can pause it where you see those formulas. Hopefully you'll be able to see me enter the formulas and you might be able to enter them a little bit easier. Okay? Assuming that I entered them correctly. Okay? I think one last thing before we completely set this off, because the next thing that you're going to do would be turning in your reports. So let me get, nope, not that. What do I expect to see in your results and calculations? Okay. So part A. I expect a trial concentration of iodide, peroxide, rate. Okay. Why do I need that? Because you needed that to be able to determine the orders for the reaction. So I need to be able to see all of those results. Okay. Everybody's experiment should be roughly the same, okay, because you all followed the same procedure. So I will go through and just compare between individual reports and say, yeah, do they look the same? Ballpark, because some of them will vary a little bit. Okay? So we would have one table. Because this is a table, it needs to have a title. It's a good thing I left lots of space for me to do this. We would have table 1 and a title. What is that title going to tell me? Something about what that table shows. Give me some information from that. Okay? After that table, you'll follow it up with a bunch of calculations. Calculations that I want to see. I want to see a general format for how you calculate the concentration of I2. I want to see it written out generically, and I want to see it with numbers. I do not need to see a calculation for concentration for iodide or peroxide. Why not? It's an easier version of the calculation for iodine. Okay? So I will assume that if you get the iodine concentration correctly, you can also get the concentration for iodide and the peroxide on your own. So I'll let that slide. Okay? Next calculation I want to see would be a calculation for rate. Generically, should be very, very simple. What's your generic formula for this? No, not quite yet. Concentration of I2 divided by time. Give me one calculation with numbers. Okay. That now gives me how you got all of the information in table 1. Okay. So I now have a way to understand where your numbers came from. As long as you didn't do any calculation mistakes, I can trust all of your numbers. Okay. If you think you're going to make calculation mistakes, then you should probably show me more calculations. Okay, but that's kind of your call. The next section of this, what would you do with this table?
Graph it.
Not quite graphed it, but pretty close. We'll show 2 graphs. Okay, because these are graphs, these are technically called figures. So we'd have figure 1 and figure 2. Those should have some descriptions of what those graphs show. I don't want a title on graphs. I want a figure subheading. Your graph should have X and Y axes labeled. Not X and Y, please. Tell me what those X and Y axes are. What did you actually plot? So for the first case, it might be on the X-axis, the log of the concentration of iodine. On the Y-axis, it would be log of the rate. Okay, so make sure your axis labels are on there. Okay, why did you do those? Well, that's where you'll show me some calculations. I guess that looks right. Your calculations are going to be generic for both of these. You're going to say the rate equals K times the concentration of iodide times the concentration of peroxide to your P and Q power. Under figure 1, if figure 1 was to solve for P, what calculation would I expect to see under figure 1? That would be your rate equals a new rate constant. So we'll call figure 1 the iodide times the concentration of iodide to the P power. What calculations are you going to show? Log a rate equals log K iodide plus P, log of iodide. You can then tell me M equals P. So you go back to your plot, and since you fit a straight line to it, you can tell me that P equals whatever your slope was off that line. Under figure 2, what do I expect to see? Very similar calculations, except now you're going to swap out iodide for peroxide, your H2O2. Okay? What does that then give you? We've got now rate equals K times our iodide to some number. We'll have peroxide to some number. One sample calculation, K generically, rate over iodide, number, H2O2, number. Put more numbers into it. You've now shown me a sample calculation for the rate constant. Since you need to show the rate constant for each trial, it could be a bit tedious to make another graph, or another table. Go back to table 1, add a new column for your rate constant. Provide the rate constant for each of those trials. The very, very bottom of that, you could then say your average. Okay. Lots and lots and lots of calculations. Okay. Most of it is just algebraic manipulations, just trying to prove that you know how to do it. Okay. At this point now you're just trying to prove that you listen to me, either in class or on YouTube later on. Okay. This is the calculations for just part A. So part B, what are we going to get from part B? For part B, you've got to go through and do the exact same calculations, except now we don't have to do orders. I will trust that you know how to do rate constants, so I won't worry about seeing that one added to your calculations. So we'll have now table 2. We'll stick with that. With a new title, we'll still need the trial numbers, the concentrations, the rates, the rate constant, and temperature. Okay. I will then be able to presume, particularly since we've talked about it so much, that the next thing you show me will be the graph. And on that graph, we'll have now another heading or sub-footer thing to it, figure 3, with some description about it. What are we going to plot on that? 1 over t and was it natural log? Log. It's natural log, right? Of k. What are your calculations that you would show after that? So the first one, why did you plot that? And because I told you so is not a good answer. So I'll stop you, a couple of you thinking that. I now know why you plotted that. You can then tell me that m equals negative EA over R. EA equals the negative slope times R number. How many times do you do that calculation? There's 7 trials, right? Should you do it 7 times? No, why not? There's only one slope. You use those 7 trials to make one slope. There's only one activation energy you can calculate because there's only one slope off your data. Next calculation, ln of A equals B. A equals e to the B. Another number. Okay? Easy, right? Okay, so those are all the calculations and what I would expect to see in the report. Okay, so this is a lot of stuff to go through and do, but that's one of the reasons why we walked through and I talked about each of these steps. You are more than welcome to show more than this. If you show less, you're welcome to do that as well, but you will lose points. Okay? This is the bare minimum as far as your results and calculations go. Now that you've finished your entire experiment, you can go back, write your abstract, include your results, and decide did you do this successfully or not. Okay? Any questions?